All right, welcome back again for this new session. So our next speaker is Atılım Güneş Baydin, who is a departmental lecturer in machine learning and a lecturer in computer science at Oxford. He's done a lot of work on probabilistic programming, including in the compilation of a probabilistic program, inference for probabilistic programs, and also a lot of work that I find very exciting on application of probabilistic programming to a variety of domains, but including scientific applications.
It was a bad idea to touch it.
Yeah, okay. It's back. And so he's going to talk about this topic today. The title of the talk is Probabilistic and Differential Programming in Scientific Simulators. And, well, welcome Atılım.
Right. Thank you, Jean-Baptiste. All right, so I think some subset of you have seen like versions of this talk before, so I was slightly worried that maybe I'm doing too much repetition. So the first quarter of the talk will be about like some technique we developed to make like using existing large-scale simulator codes as probabilistic programs. Then the rest of the talk is actually very application-heavy. I do like lots of collaborations with people who work with simulators in different fields of science. So it will be mainly like a survey of like what's possible, like using probabilistic inference in existing simulators in various fields of science. So let's start. Is this working my way? No, okay. Yeah, I can't switch slides, but I can just point to things, I guess. Yeah, so the outline is, so I have a part where I talk about how to repurpose existing simulator code bases as probabilistic programs. And there are some extensions you can do like after that, like completely getting rid of the simulator and replacing it with a deep learning based surrogate of the simulator. After that, I'm going to talk about differentiable programming with simulators. For example, learning a differentiable surrogate of the simulator, or if your simulator's source code allows, you can do automatic differentiation of the simulator code to get the differentiable version of the simulator. And so I'm going to talk briefly about a project called F# that I've been working on. It's a differentiable programming library in F#. And I'm going to like introduce like very quickly a couple of events we are organizing to basically bring people together from probabilistic programming, differentiable programming, and physics communities to basically like start collaborations of the sort like I'm going to present. If people are interested in being involved, like that's an opportunity for actually like participating in the community. Yeah, so let's talk about the probabilistic programming bit. Yeah, simulation is useful or like a central tool in many fields of science, and these range from particle physics to cosmology, like in all scales of science, basically. There are interesting ways of bringing together simulation and probabilistic programming together. They have lots of things in common. So the idea is basically, so I'm thinking about maybe taking the risk of doing this. Okay, so I can just maybe switch slides before moving too much away from the microphone. Can I do that? Yeah, I don't want to be that person who touches the microphone the whole time. Okay, can we do it? Does this work? Okay, perfect. Yeah, so to basically introduce what type of thing I'm talking about, think about the simulator as like a black box that does something for you. It takes some parameters, it does some sort of like physical simulation in many cases, and it produces some output. And so you can run this forward, and that gives you like simulated data, obviously. And this is useful in like many application fields where you want to project things into the future. You want to predict things like how a protein can fold, or how like climate models can behave in the forward time direction. But in many fields of science, you are actually interested in the opposite direction. So you are interested in doing inference, basically. So that means that we have some data that corresponds to the output of the simulator, and you want to do inference to say something about the parameters or internal quantities in the simulator that are like consistent with the observed data. This is exactly the subject of the probabilistic programming field, if you noticed. Yeah, some examples I usually give are like seismology. You have a model of how seismic waves go like in Earth's crust. So you have some measurements and you need to infer like the initial locations and characteristics of earthquakes maybe. In particle physics, which is an area I've been working in, you have like very large scale experiments measuring data in large like particle detectors, and you are supposed to infer what's going on inside these detectors. These are literally latent quantities that you are trying to infer from data that you observe in your particle detector. So probabilistic programming is the perfect tool for this sort of like inversion and inference problem. One thing I usually say is that in my view, some people might object this, but I think that probabilistic programming has been somewhat limited in scale. In general, like people work with toy scale or small scale-ish problems, and I think this is mainly because you need to implement things from scratch. You need to like adopt the probabilistic programming language or system, and you need to sit down and implement your models in that system in order to do inference. So one idea which might be like maybe obvious in retrospect is if you have some stochastic code, such as a simulator, let's say it's a very large scale simulator, like millions of lines of C code, let's say. It has some stochasticity in it. Many simulators do, because that's what makes them interesting. So there's some sort of random number sampling happening inside the simulator. So the idea is, can we go and capture that random samples and treat them as samples from an implied prior distribution? Basically, that's the basis of the whole like first quarter of the talk. So if you have access to the source code of the simulator, you can say that the stochastic simulator is a probabilistic program. You need a bit of extra work and some sort of infrastructure to actually execute an existing simulator as a probabilistic program. So we have some prototype system called PyProb. This is a Python-based yet another probabilistic programming library specifically designed for making this sort of things possible, like working with existing simulator codes. Basically what's happening is we have some sort of protocol or interface to which we connect the source code of the simulator. In many cases, this just means you go in the simulator's code base, find the places where, or find the place. This is usually a single source code file where the probability distributions in that simulator are defined, like a place where you define your Gaussian, Poisson, whatever, all sorts of like distributions. Instead of using the language's random number generator, you just redirect that to a call from a library we created. So that just takes care of connecting the source of randomness of the simulator to the probabilistic programming system running in Python. So that's what I mean by running the code forward and catching all random choices. So once that happens, we are able to record these execution traces. So that is done through this protocol we call Probabilistic Programming Execution Protocol, or PPX. That's language agnostic. It's basically some protocol based on Google flat buffers that have like that is a compiler that gives you all the code you need in any of these languages to connect to the probabilistic programming system. So this is somehow like an analog of the Open Neural Network Exchange protocol that people use in the deep learning community to exchange models between, for example, PyTorch and TensorFlow, serializing and deserializing models. So this is maybe something like a probabilistic programming analog of that type of thing for the community if people need this sort of stuff. So there is this addressing concept. I won't go into that because it always it's a bit like a lost cause when you have limited time in the talk to talk about how to do like the addressing and uniquely labeling each random choice in a simulator. But if people are interested, we can talk about that. But so here I have an example. This is in C++. Basically, you get stack traces, and you concatenate lots of stuff, basically keeping a history of the whole sequence of function calls that happened until the point where you ended up getting some sort of random number. In this case, it's from a continuous uniform distribution. So once you have all this capability, basically you run your simulator unmodified except for like redirecting this randomness to the probabilistic programming system. You run it as usual. As a side effect, you get execution traces. So that's the basis of like combined with a way of doing conditioning and like so the ingredients you need are like execution traces, the sampling bit, and you also need some sort of conditioning facility. It means that you need to define a likelihood or like something like that. Once you have these two ingredients, you can do probabilistic programming. And so in this system, we have importance sampling and MCMC algorithms implemented. And we work with some fairly large-scale simulators. So once you do that, you get something that looks like a probabilistic program, but these things are really huge, like really big, because the people who wrote the simulator had no plan or intention to write a probabilistic model. Basically, you are taking the code and treating all sorts of like random samples as samples from prior distributions. So you end up with tens of thousands of latent variables, and this is obviously a problem, and it's actually the biggest problem affecting the feasibility of this sort of thing. And one thing you can do is amortize inference, meaning you can use some sort of deep learning-based proposal mechanism to make inference a bit more, or maybe more than a bit more efficient or like feasible. So this is supposed to explain how that works. Maybe it's a bit overly complicated, but so there are two phases. There's a training phase. This is the costly and difficult phase. Basically, you run your simulator lots of times. You record the pool of execution traces recorded through the protocol that I described. Imagine you run your simulator probably in parallel on many machines, and you have a pool of millions of execution traces. And this is like a Turing complete thing. For example, there was a mention that the stand doesn't support like things being different in each iteration. So here we are not in that type of setting. Basically, if this is like, let's say it's a C++ code. Every time you run it, it gives you a trace of different length, different things in different orders. So the trace space is really complicated. Sometimes the variable exists, sometimes it doesn't. All sorts of things are possible. So you have this pool of execution traces characterizing the whole like probabilistic behavior of that simulator code. And what we do with this amortized inference thing is, so this orange node here is representing some observable variable, whereas the others are latent variables, let's say. And this is usually in the end of the simulator. So we do the inversion where we are actually training a neural network. And this is a recurrent neural network, like an LSTM, or like a recurrent family. So you make the observable quantity from that trace the main input, like the input to the neural network, and expect the neural network to learn distribution under which the rest of the trace is likely. So you maximize that likelihood. And basically, the network learns to produce proposal distributions that are like informed by the observable quantities that you give to it. So this is extremely costly, but you have to do it only once per given simulator. So when you start working with a problem, and at the end of it, you have this trained neural network as a artifact. Initially, we called this a compilation artifact, and this method was called inference compilation. It's like a analogy, like a very costly compiler giving you something that allows you to do inference later, faster later. So that's what makes it amortized. Basically, so you have your trained neural network specialized in the simulation or simulator. So you have that thing, and you have some new observed data. This time, we make use of that trace recording facility to actually control the simulator. Basically, the neural network replaces the prior distributions in the simulator. Every step of the execution, we go to the neural network, we ask the network to give us a distribution for each random quantity that the simulator is going to produce. Basically, we replace the prior with the proposal that is coming from the neural network. Then you execute your simulator under the control of this amortized inference engine, and you end up traces where the rest of the trace is compatible with the observed data. It's in a sense that you get posterior traces that explain your observed data. This is like a very high level summary of what's going on. Another way of talking about this is that the probabilistic programming system is controlling the simulator, somehow guiding it to do interesting things. So in order to achieve this, there are two pieces of code, the project. Like this is a completely Python-based probabilistic programming library that is doing all the inference and basically all the probabilistic programming tasks. We have this protocol, which is very lightweight, that gets compiled to these languages. Basically, you can take any stochastic code in any of these languages, connect it to the protocol, and the execution is done always in the Python side by that library. Yeah, we don't have time to go into detail, but it's like a very lightweight, very simple, really way of two sides communicating to each other. So for example, this is the probabilistic programming system. This is the simulator. The probabilistic programming system tells the simulator to start. Then it starts. All the deterministic stuff is invisible. We are agnostic to all deterministic things. Like this thing can take forever. It can be something huge. The only points where we interact through the protocol are points where there is some stochasticity, something being sampled. When the simulator code needs a sample, let's say wants a standard normal sample, it goes through the protocol. Python does the sampling, does the typical probabilistic programming thing, does the bookkeeping, returns a sample value, and the simulator keeps going. The probabilistic system keeps going, so they go in parallel. So this allows two things. This allows you to record the prior behavior. It also allows to change the actual distributions behind the scenes, basically sample from something else where the simulator is expecting samples from prior, for example. So this is how a full model looks like in C++, for example, through this protocol. So you just have this header file, and this is the full thing you would need for a basic little model for a Gaussian unknown mean. At the end of the day, you start some sort of server that is serving the model at an address, TCP address or some other protocol. This just means that you can run, we always run the model and the inference engine on in different processes. These things can be in the same machine, communicating through Unix sockets. Or they can be even in like different machines. We also had to do that at some point. Like you can run the model on one machine, you can run the inference engine on the other machine, and they like on the fly run in lockstep. So that's how things look like in C++. So this is how things look like in the Python side, in the library side. So you instantiate your model by connecting to an address at which you expect the model to be served. From that point forward, yeah, you have some little bit of like handshaking. Then you can do like you can get the prior distribution of the model. You can do stuff like that are defined in the Python library. So I'm going to talk about applications. And so this whole thing started because we started collaborating with some particle physics people, and it's been like a large collaboration of particle physics, machine learning, and high-performance computing people. And the main motivation behind the work is, so at CERN, there are enormous amounts of data being produced, like so much that like most of it is just dumped without even being saved. So there's some sort of mechanism that makes a heuristic decision to like capture and record the data versus just let it go. So, so this stream of data is currently analyzed with like a very old school and like trusted established ways of particle physics people by doing histograms of summary statistics and like quite manual ways of like checking for the existing of results in a histogram or things like that. So the ultimate goal is to have like an inference pipeline that would make that type of thing more principled, or like doing something like probabilistic programming, where you can actually condition on some real data and get some posteriors in your simulation type of result, which is not something currently being done in the particle physics community. Yeah, this is supposed to actually summarize what I just said. So you have the real world where you have some mechanism producing observed data. You have a simulation analog of that, and basically you get your real data, you condition on that in your simulated world, and you get some posterior distributions. So we had like a proof of concept of this type of thing working with a very large scale simulation of the standard model. It's called, there are multiple libraries doing this. One of the popular ones is called Sharpa. This is a C++ library, about 1 million lines of code. So it was quite large scale. We were almost getting the best paper award in a supercomputing conference. I think maybe, and please correct me if I'm wrong, this might be the only case where probabilistic programming has been done in supercomputing scale. I really need to check if that's correct. Yeah, so yeah, basically we showed that this is actually feasible, and this was the first time tractable Bayesian inference is done in a LHC, or like Large Hadron Collider physics setting. Yeah, so we also had like results showing this amortized inference, the inference completion thing actually agreeing with the MCMC result. In this experiment that we had in the paper, like MCMC inference took 115 hours, whereas with the amortized one you can get a pretty close results in just like around 30 minutes. And this is an arbitrary speed up, like it just, because it's parallelizable, you can like have many more nodes and you can get this number as small as possible given your compute budget. So there are some extra things about looking at the sample traces and like thinking about or like observing the internal probabilistic structure of the simulator, because it's something that you not do normally, like given an existing simulator that people have been using for a decade, but not actually thinking about it as a probabilistic model. Basically, we are supposed to develop the tools to like look at the simulator from the perspective of probabilistic programming. Initially, things have been a bit difficult or like almost ridiculous, like because so in this sort of result we have like a handful of posterior plots, right, of some interesting quantities in the simulator. But the thing is, like, these are just like a selection of like latent variables over which we have posteriors. Normally in that simulator we encountered more than 25,000 latent variables, like over which we get posteriors. And you can do like produce graphs showing which variable is followed by which variable. So like when you do this address graphs, you get structures that correspond to rejection samplers. For example, you keep sampling something until it gets accepted and things like that. That's a bit cool and interesting, but it doesn't get you a lot in terms of interpretability. There are ways of simplifying these graphs. Basically, just you have instance counters. That is a part of the addressing scheme. Basically, if you have something repeated all the time, you can collapse that into one node. And that actually gives you something that captures the probabilistic structure implemented in the simulator. And you can do that with different resolution or granularity. For example, if you look at the 10 most common types of trace you can get in the standard model simulator, you get this sort of structure. There's the start node, there's the end node, and these are like addresses that always follow each other. And like sometimes you have loops. This is a rejection sampler, for example. You get you sample several stuff. You sample something that has something to do with the acceptance criterion, let's say. Then sometimes you accept, sometimes you go back, or like you can interpret things this way, and you can get like a more and more detailed picture of what's actually going on inside the simulator as you like take more trace types into account. Yeah, so that's one extra benefit you can get from this type of thing. So one extension you can think about is this structure actually looks very interesting. Can you do other things with this? For example, can you use this as a substrate on which you can construct deep learning models that can actually approximate the behavior of the simulator and keeping the same address space and like the same structure? Like basically you distilled the whole probabilistic structure of the simulator that you can use for other purposes. So in some work that I think actually got recently accepted to UAI, we basically do that. Andreas Monk did that actually. And he also made this like super crazy complicated figure, which I'm going to try to explain. So the thing on the top is these two pieces. So you have your probabilistic program, let's say, and you have this inference network. It's an LSTM. So every time you run some sample statement, there's an address associated with it that goes to the network. We just tell the network, OK, I need a sample for this address. And the network gives you that. And the network is recurrent, meaning it keeps a state that actually corresponding to what's going on in the history of the program execution. So the summary is, with the data you already sampled, that trace data, you can do something that actually replaces the simulator itself with the same address structure. So you keep the structure around, you don't discard the simulator, and you can replace the whole thing with some like deep learning based, I don't know, thing that actually remembers some core aspects of the simulator, namely the addressing scheme and what gets followed by what and things like that. So that's basically what's going on in this work. This is what we call a probabilistic surrogate network. So in summary, like this was the previous figure. So you train like the inference network. Then for inference, you use that with new observed data. In this new version, you can train the proposal network and the surrogate network together. Then at inference, you can use the surrogate, the inference network, and the new observed data. And the surrogate replaces the simulator. You have some completely deep learning based system where you produce results that are indistinguishable from those coming from the original simulator. Basically, you get rid of the simulator. This has a lot of advantages in terms of speed and other things, maybe differentiability, and you still have behavior that actually corresponds to the behavior of the simulator. So I do other collaborations in different areas I don't have time to cover. One is about spacecraft collision avoidance. Here you have physical models of how spacecraft move in orbit, and you need to predict the probabilities of collision between objects to make maneuvering decisions. This is in collaboration with the European Space Agency. And the other thing I was talking to Maria about is actually about simulation of misinformation dynamics in social media. This is something we are doing with the Swapnil Mehta from NYU. It's basically using probabilistic programming to model the spread of information. Instead of trying to label things as misinformation or not, which is a very difficult thing, you can actually try to model the whole behavior based on expert knowledge, and do things about you can compare maybe different ranking or recommendation algorithms and their effects on how information spreads in the network. Yep. So I'm coming to the differentiable programming bit, and I'm going to speed up a bit. Sorry, Jean-Baptiste. Yeah, so this differentiable programming thing, for people who don't know about that, it's about, it's the basis of what's going on in machine learning. Most of the things in machine learning are based on gradient-based optimization. And these gradients are coming from a technique called automatic differentiation. It's a way of taking some sort of source code and making it differentiable. So differentiable programming is a new term referring to deep learning, or a generalization of deep learning, where you define differentiable and parameterized building blocks. You construct complicated models, then you optimize the parameters. This is exactly what people are doing in machine learning. It's just a new name for this thing. And the realization is that neural networks are not spatial. Neural networks are just a spatial class of historically interesting differentiable functions. So in the simulator domain, there are two things that can happen. Your simulator can be not differentiable. In this case, you can learn differentiable surrogates, or it could be differentiable but has not been differentiated yet. You can attempt automatic differentiation to take the source code and make it differentiable. Yeah, I should maybe speed up, but the idea is basically I'm just going to cover these two cases. So if your simulator is non-differentiable, you run it lots of times. You define some sort of probability distributions over quantities with respect to which you need derivatives. So you sample a large data set, and from this you can learn a differentiable approximation of the behavior of the simulator, which is quite like what we did in the first part. Basically, using this surrogate, you can do design optimization. In this work, for example, we optimized the muon detector, the shapes of some magnets in a particle physics instrument, based on some differentiable surrogate of some existing simulator. So I had work in exoplanets. Basically, they have very slow radiative transfer models. You can learn a surrogate. You can make it around 180 times faster, and you can do Bayesian inference with this fast thing that enables inference, computational cost-wise. And lately, I'm working on data from Parker's Solar Probe. This is basically taking another simulator, in this case called EPRAM. This is extremely slow. We learn a surrogate that is about 1 billion times faster. This is quite typical, by the way, in many fields. When people do surrogates, they encounter 1 billion speed-up factors. Almost ridiculous. So basically, the idea is to get these surrogates, because they are faster. You can do things like important sampling. You can get like millions of samples in some like feasible time. So if you have differentiable simulator, you can actually, I'm going very fast, but you can do automatic differentiation. You can have source-to-source transformation of the simulator to get the differentiable version of it. So I don't have results in this area, but there is actually effort to do this sort of thing for large-scale pipelines in particle physics to design optimization. And so I'm going to refer to one event at the end of the talk that actually wants to bring together computer science and physics communities to work on this sort of problem. Yeah, so this is an extra subject. So I work on a library called diff-sharp. It has been dormant for a while. This is something I do with Don Syme at Microsoft and now at GitHub. Basically, this is an F-sharp-based differentiable programming library that does some like nested higher-order differentiation stuff with a very complicated API supporting lots of things. Basically, Don and I have been working hard to re-implement lots of things. This thing now supports tensors properly based on PyTorch's C++ and CUDA like core. Yeah, so this is basically something like an advert for people who have an interest in maybe trying out things like new like probabilistic programming work in F-sharp language. And it has support for Colloque and like all sorts of modern like tools that people could not use before with F-sharp. I have some like very little toy library, yet another probabilistic programming library implemented in F-sharp based on F-sharp. This is a little preview of that. Yeah, so this is the part where I talk about these two events and maybe invite people to like come and join this sort of thing if you are interested. One is with people basically involved at like experiments at CERN, like with lots of institutions. This is called the Machine Learning Optimized Design of Experiments, or the MODE collaboration. There's a website. We organize some workshops specifically about like optimizing physical, like large-scale experiments with differentiable machine learning approaches. The abstract submission is in 2 days. I don't know if you can make it, but like you can, yeah, I don't know, go for it, Jan Willem. I heard you're interested maybe. The other thing is, there is more time for this because this is next year. So this is a program that got approved by Munich Institute for Astroparticle and Biophysics. So this is going to take place next year in June, almost a whole month. It's like a program where you get hosted, and you are actually supposed to engage the community on the other side. Like if you are a computer scientist, you can engage physicists. If you are a physicist, you can engage computer science people, basically to start working on collaborations that involve the types of applications I've been talking about. So, and actually the probabilistic programming is in the name. So it should be very interesting for the, I mean, I'm just making an assumption, but it could be interesting for the probabilistic programming people here. So yeah, that's basically it. Thank you.